On some of the graphs that we've seen already, we've calculated the instantaneous velocity, meaning the velocity at a specific moment in time. Now, we took that from the average velocity, right? If we had a single straight line, it meant constant velocity, and we found the average velocity on that single straight line to be 5, then the velocity anywhere along that straight line would be 5, and therefore the instantaneous velocity at any point would be 5. Now we're going to deal with finding instantaneous velocity when it's not a single straight line, but rather when we have a curved line. To do that, we're going to have to draw what we call a tangent line. Now, right now, that probably doesn't make much sense to you, that word tangent line, but I'll show you what I mean by that in just a second. Just remember that when you have a straight line, the instantaneous velocity is the same as the average. When you have a curved line, the instantaneous velocity is not the same as the average. We have to draw the tangent line, and then we calculate the slope of that line using rise over run, or saying v is equal to delta d over delta t, which corresponds to the slope. Here's an example. It says, what's the instantaneous velocity of the object on the following graph at 6 seconds? So here's what we want to do is draw this tangent line at 6 seconds. Just put a little point, a little X, a little dot, something at 6 seconds, first of all. Now, a tangent line is a line that approximates the slope of the graph at that one spot. It's always a straight line, and you should always use a straight edge. Ideally, it's a clear straight edge, like a clear plastic ruler, because it's a little bit easier to draw it if you can see through your ruler, but it doesn't have to be, as long as it's a good straight edge. Don't use like the edge of a piece of paper. Okay, use something that's legitimately straight, and like plastic or metal or something like that will allow you to do a good straight line. Now, when I draw my tangent line down here, it's difficult to do. I'm going to try to use the straight line function on the smartboard here, but it's harder to do on here than it is on a paper. So bear with me for a moment here, okay? This is my straight line function. My straight line should be drawn. That is actually not bad. That is not a bad tangent line, actually. That approximates the curve, the slope of the graph at that point. Notice if I was to draw it like this, that's a straight line, but that bears no resemblance whatsoever to the slope of the curve at that point. You want to make sure when you're doing this, as best as possible, that your tangent line cuts through only that one spot. Now, if your graph does happen to go around like this, on another curve, it would be okay to intersect that, but you don't want your tangent line to intersect the curve that you're finding the tangent line for. Does that make sense? Yep. Like run along it? You want it to touch one point. Ideally, you're touching one point and just one point. Now, mine's not perfect because you can see it's kind of touching a couple points before and a couple points after. That's okay if it's a little bit before and a little bit after, but theoretically, it should just be literally 1 point. Now, you're not going to be perfect with this, but you want to be as close as possible to touching 1 point. Now that I have my tangent line drawn, I got to do something with it. We said in the notes that we take the slope of that graph. Well, the slope of the graph is rise over run, right? But it's also, when finding velocity, average velocity, meaning slope, we can always use v is equal to delta d over delta t, displacement over time. That's the same as the slope. So you can think of it any way you want. To do that, you're going to pick 2 points. Ideally, 2 points that are far apart. Maybe this point and maybe this point right here. I'm going to say v is equal to delta d over delta t, but if you said slope is equal to rise over run, it would give you the exact same thing. D is, well, we're going to say d2 minus d1, or df minus di, same thing, over tf minus ti, or t2 minus t1, right? M is equal to delta y over delta x. V is equal to delta d over delta t, exactly the same thing. Now, my df here, it's hard to see it on the board here, but it looks like my df is about right here, which is about 440, 480, about 520. Yours is going to be different depending upon where you picked your point. So you're not necessarily looking for the exact same numbers in your equation as I am. You're just looking for the same answer, more or less, as I am. I'm going to say my final position is 520. My original position, if I went way down here, is 0. My final time is 8 seconds. My initial time is, what is that, 2.4, 2.8? I think it's about 3. About halfway between 2 and 4. So we're going to say it's 520 divided by 5, which is going to give me 104 meters per second. So the instantaneous velocity on this line at this point at 6 seconds is about 104 meters per second. Now, I want you to calculate yours. Yours are all going to be a little bit different than mine because your line of best fit isn't going to be the exact same line as mine. My line of best fit isn't perfect. I don't expect your line of best fit to be perfect. Okay, that means we are going to have a little bit of variation in our answer, but it shouldn't vary by that much. Okay, do that now. Don't worry about my numbers here. Okay, calculate your slope or your v is equal to delta d over delta t, and let's see how close you get to 104. I'd like you to take a look now at worksheet number 3 that you've been working on, but the last question now on that worksheet, what's the instantaneous velocity of the object at 6 seconds? So draw your dot at 6 seconds. Some people were doing that in the example. Put your dot there. Draw your tangent line and do exactly what we just did, right? My tangent line is going to look something like this. Okay, then pick 2 points on that tangent line, preferably far apart on that tangent line, and then do your thing with slope or v is equal to delta d over delta t.